The next concept that I want to talk about is the rate law. Now, rate law is just a mathematical way to show how changing the concentration of your reactants will affect the overall rate. So here, the variable that we're looking at more closely is concentration and how that affects the rate of the overall reaction. Now, generally speaking, we know that if you increase the number of reactant particles, then we've got more collisions. More collisions means that you are going to increase the rate of the reaction. That is true in majority of cases. So here what they've got is we've got a generalized reaction here where you have your reactant X and your reactant Y, and these happen to be the mole values for each. So those would be representing your coefficients, yielding some sort of product. Now, when we're looking at how the effect of concentration affects the rate of the reaction, we really don't care about the product because it's the initial reactants that are of utmost importance. So what we want to do is we want to figure out how altering the concentration of each reactant separately will affect the rate of the overall reaction. So what you have to do is you have to come up with a generalized rate law. Now, rate law is expressed like this, where you have the rate is equal to some sort of rate law constant, which we will give the letter lowercase k, times the concentration of your first reactant raised to some sort of exponent, times the concentration of your next reactant raised to another exponent, and you could even have more reactants in this case here. So if we take a look at this first reaction of hydrogen peroxide yielding, which is decomposing into water and oxygen gas, we notice that the rate law constant that has been figured out experimentally looks like this, where you have the rate equals to some sort of constant K times the concentration of that reactant. Now, in this particular case, the exponent was established to be a 1 experimentally. So we don't assume that the coefficient becomes your exponent, okay? So what they want to know is what would happen to your rate if you were to double this concentration. So if I make this a 2, you would say, well, 2 to the power of 1, the rate would double. If you were to make this a 3, if you take triple the concentration, 3 to the 1, the rate would triple. So we call this a first order reaction. So we would see that the rate is directly proportional to the concentration in terms of yielding a linear relationship. So doubling this would double the rate. If we take a look at the next reaction, we notice that the rate law constant has been established to be K times the concentration of this reactant to some sort of exponent 2. And again, it just is sort of coincidental that these happen to be the same value, but we don't just assume that that is the exponent. So here, if I was to double this concentration, so let's say that I put a 2 in here, 2 to the power of 2 means that the reaction would be 4 times faster. If I was to triple this concentration, put a 3 here to the power of 2, it would be 9 times faster. So this would be called a second order reaction. And what that does is it causes your rate to sort of rise exponentially as the concentration is doubled or tripled. The rate is exponential to that concentration. So let's take a look at some experimental data. Here we have a reaction of nitrogen oxide plus hydrogen yielding nitrogen gas and water. And what we want to do is we want to write a generalized rate equation for this reaction. So what we would do is we would say R, the rate is equal to some sort of rate law constant times the concentration of reactant A. Okay, we'll call this reactant A. And I can choose any sort of letter to represent my exponent. And I'm going to multiply that by the concentration of my second reactant to some sort of exponent. And I'll just pick the letter Y. So what we want to do is we want to see the effect of changing the concentration of this reactant, what effect it has on the overall rate. And in order to do that, you have to make sure that the other reactant is being held constant. So somebody carried out 6 reactions, and what they did was in the first 3 trials, they changed the concentration of the first reactant, NO, and they held the second reactant constant. And they wanted to see how did doubling, tripling the concentration affect the rate. And we can see here that when I look at trials 1 and 2, I doubled the concentration. So what do I notice happened to the rate of my reaction? Well, it went 4 times faster. If I take a look at how did tripling the concentration, what did that do? Well, I see that it went 9 times faster. So I want to think about what is the order of my reaction. Will my exponent be a 1? Will it be a 2? Will it be a 0? Now, if it was a 0, it means that it would have no effect. So what I can do is I can look at it and intuitively come up with the exponent, okay? Or I can set it up like this. So I can take a look at trials, and what I want to do is I'll pick 2 trials where the NO is changing, H2 is held constant, and see the effect on the rate. So what I do is I will pick trial 2 and 1, and I'm going to divide trial 2 by trial 1. So I take a look at the concentrations at trial 2, 0.002 moles per liter, and I divide that by 0.001. So what I did was I took the higher concentration divided by the lower concentration to some power of x, because that's the exponent that I decided to pick for that particular reactant. Then I take a look at the rate. And because I did trial 2 divided by 1, I have to take the rate of trial 2, and I divide that by the rate of trial 1. And what I see is I have 2 to the x equals 4. So what I do is I figure out 2 to the what equals 4. 2 to the 0? Nope, 2 to the 0 always equals 1. 2 to the 1 would give me 2. 2 to the power of 2 gives me 4. So in this case, the exponent for my nitrogen oxide reactant would be a 2. So it's second order in that particular reactant. If I want to see the effect of the next reactant, I have to find 2 trials where reactant 1 is being held constant and reactant 2 is changing. So I could look at trial 4 and 5, because these are held constant, these are changing. I could do trial 5 and 6, or I could compare trial 4 and 6. Okay, it doesn't matter. So what I'm going to do is I'm going to take a look, and again, I'll do the same sort of method that I did before. So if I happen to take a look at trial 5 divided by trial 4, okay, what I'm going to see is I have a change in concentration of 0.002 divided by 0.001 for that reactant. So again, we're looking at H2, the effect on H2. And I take a look at the rate for those trials, and we see that the rate is proceeding at a rate of 0.016 moles per liter times seconds, divided by 0.008 moles per liter times second. And I noticed that 2 to the y, and again, I chose y because that's the arbitrary letter that I chose for that particular reactant. And I divide those, and I see 2 to the y equals 2. What value would I pick? Y equals 1. So we would say that the order for this particular reactant is first order. So when I rewrite out the rate law, R equals some sort of rate law constant times NO reactant to the power of 2 times H2 reactant to the power of 1. So let's just take a look at what I've written there. And here, when we double this concentration, the rate goes 4 times faster. If I double this concentration, if I put a 2 there, it goes 2 times faster. So the overall rate, what we do is we add the 2 exponents together. So the overall rate is an order of 3. So rate order of 3. What we would do is if I doubled this and I doubled that, what I would do is I would say, okay, 2 to the 2 times 2 to the 1. So this would be 4 times 2. So your overall rate would be 8 times faster. Now, let's take a look at how to solve for this rate law constant. So what we want to do when we're solving for the rate law constant is we want to pick any trial. Now, I usually just pick trial 1, the first one that's listed, and I'm going to start substituting in these values into that overall rate law that I established. So in rewriting the overall rate law that I had mathematically determined, here it is here again, what I'm going to do is I'm going to substitute the values in from trial 1. So the substituted value for the rate at trial 1 is 0.002. And again, I got that right from here. And then I take the concentration for trial 1 for nitrous oxide, and there it is there, it's 0.001. And I raise that to the power of 2 because that's the exponent that I mathematically determined, times 0.004 to the power of 1. What I would do is I would go ahead and I would plug that into my calculator, and you're going to see that this is what I ended up determining. So when I square that, this is the value that I get, and this to the power of 1, that is what I get for that answer. I multiply those out, and I get 4 times 10 to the negative 9. My rate is still to the left of the equal sign. When I want to solve for k, I want to bring this value to the other side of the equal sign, doing the opposite operation. So I'm going to divide by 4 times 10 to the negative 9, and I end up getting a value of the rate law constant equal to 500,000. So I know that that seems like a really big number. Now, what I now know is one more piece of the puzzle. R equals 500,000. Okay, now I'm going to leave a blank here because we have to still solve for the units of k. But I know the exponent for this concentration is a 2. This exponent is a 1. Okay? Now, how do I go about solving for the units for k? Now, I tend to do the units separate from the numerical values. So what I do is the exact same thing that I did here, except instead of using numbers, I use the actual units. So the units for rate, we know, are moles times liter to the negative 1 times second to the negative 1. What I've done is I've taken my numerator and I've raised those to the negative 1 so that they become take my denominator and made them become a numerator. What I do is I'm going to let k equal the units that I'm solving for. We know concentration is always in moles per liter, which is the same thing as saying moles times liter to the negative 1, and that happens to be squared because there's a 2 there. Now what I'm going to do is multiply that by moles times liter to the negative 1 because that's representing the concentration of H2, and that's to the power of 1. Now, knowing our exponent rules, what you want to do is you want to make sure that you apply those exponent rules to those units. And so what we do is that becomes moles to the 2 times liters to the negative 2 multiplied by moles times liter to the negative 1 because the 1 just remains the 1. Again, on the other side, I still have my rate written like this. Now what you want to do is when you are multiplying your units together, we must add exponents. That's your exponent rules. So on the right, this becomes moles to the 3 times liters to the negative 3. And again, on the left, I still have this written out for my rate. Now to solve for k, I'm going to leave k where it is. I'm going to bring this to the other side. So when I divide moles times liters to the negative 1 times seconds to the negative 1, I'm going to divide by moles to the 3 times liters to the negative 3. And remembering your exponent rules again, what you want to do is when you are dividing, you are going to subtract your exponents. So moles to the 1, because remember there is no value there, so we just assume it's a 1. 1 minus 3 becomes moles to the -2. -1 subtract -3 becomes liters to the +2, okay, because a negative minus a negative, okay, and then we still just have seconds to the -1 because there is nothing in the denominator, equals K. And what we want to do is we want to rewrite this so that all of our exponents become positive values. So here, K is equal to liters on top squared divided by moles squared times seconds, okay? So those are the units for K. So when all is said and done, I go ahead and I take those and I rewrite them into this spot here. So that becomes liters squared over moles squared times second. Now, it's kind of weird that with every reaction, even though this is called a rate law constant, the units for that constant are always changing. It all depends on the order that was established for each of your reactants. So now what can happen is we can actually mathematically determine what the rate of this reaction would be if I was to throw in any sort of concentration. So if I go back here, it asks me to figure out if I had a concentration of this, of 0.018 moles per liter for NO, and I put that into my rate law constant. And if I have 0.046 as the concentration for my H2, what I would do is I'm going to substitute those values in. So here, if I have 0.018, I'm going to square that value. Okay, so squared. I'm going to multiply that by the concentration of 0.046. I'm going to multiply that by 500,000. And there we go. And what that is telling me is that the rate will be 7.452 moles per liter times seconds. So that's a lot to take in. It looks pretty mathy, but what I would do is I would break it down into your numerical values, solve for your K value that way, then solve for your units separately, plug it all back in, and you have your overall rate law.